Hi guys, in today's video we're going to be taking a look at a simple pendulum. So let's go ahead and draw out our scenario. So we're going to have some ceiling, and what we're going to do is attach a mass M to some string of length L. So this will be pulled at some angle theta, and then when we let go of this mass it should really oscillate around this equilibrium position, which is sort of this vertical here. So what we want to ask today is this simple harmonic motion, or is this some other more complicated harmonic motion? So in order to do that, we sort of remember our first condition for simple harmonic motion is that there has to be a restoring force, which is always going to be pulling this mass towards the equilibrium position. So in order to see that here, let's go ahead and break up our free body diagram. And we see we have some tension force along the string at any given time. And then we will also have a gravitational force. So I'm going to go ahead and break this gravitational force up into its components, as we often do. And so in this case, we also see that's an angle theta. So here we are concerned with finding a restoring force, which should point us towards this equilibrium position. So first we want to note that the tension force and this green component of the gravitational force are really radial forces. So that means they are going to work to keep this moving in circular motion, to keep this moving in its arc. So we're not going to be concerned with those today. What we're concerned with is our restoring force. And so here we see that can be, that is really this gravitational force, the tangential component. So this T stands for tangential. So this red component here is going to be acting as our restoring force. So we see that no matter where we draw this free body diagram, this tangential component of gravity is always pointing towards that equilibrium position. So really we sort of have our first condition met, which is that our tangential component of gravity is equal to our restoring force. And from this triangle here, we can see that that also should equal Fg times sine of theta. So now our second condition for simple harmonic motion is that our restoring force should be proportional to our displacement. Right? Recall Hooke's law. So in this case we see that's not quite true because our restoring force is actually proportional to sine of theta and not theta itself. So we can get around that by saying, well, if our angle is small, so if theta is small, then sine theta is approximately equal to theta. This is in radians, this is true. And that's called the small angles approximation. And I say again, this is only if theta is small. So we need our angle to be small. So the small angle approximations hold as long as the angle that this pendulum swings through is small. So if that's the case, then we can say that this is actually really equal to Fg times theta itself. Sine theta is just approximately equal to theta. And at that point we see we do have our second condition met, because then our restoring force is indeed proportional to our displacement. So we see then we really are sort of relying on an assumption. Assuming that the angle this swings through is small, we can call this a simple pendulum. And so assuming that all of that is true, we can derive some things using our knowledge of simple harmonic motion. And we then get that our frequency is going to be equal to 1 over 2 pi square root of g over L. And then our angular frequency simply will just be square root of g over L. So these are some quantities we'll use today, and again this is only true assuming that we do have the small angles approximation and this is a simple pendulum. So let's go ahead and look at the problem statement. In the figure below, the upper ball is released from rest, collides with the stationary lower ball and sticks to it. The strings are both 50 centimeters long. The upper ball has a mass 2 kilograms and is initially 10 centimeters higher than the lower ball, which has a mass 3 kilograms. Find the frequency and maximum angular displacement of the motion after the collision. At this point, you should pause the video, reread this problem a couple times, and maybe even try it on your own. Okay, so we have our scenario drawn out right here. So let's explore real quick what is going to happen here. So once we drop A, it's going to fall down, collide with B, and then they're both going to sort of swing in some pendulum motion. So of course, at the moment, we're not sure if this is going to be able to be approximated as a simple pendulum or if it's going to be a more complicated motion. Recall, if this angle that it's swinging through is small enough, then we can use small angles approximation, and this will be a simple pendulum. If it's too big, then that's not really valid anymore. But let's go ahead and start off and just recall, if it is a simple pendulum, we automatically know that the frequency of a simple pendulum is given by this condition. And so we have the gravity and the gravitational constant and the length of the string. So we can go ahead and just plug those in, and we can solve directly for our frequency, assuming this is a simple pendulum. And so if we assume that, we get a frequency of 0.705 hertz. And that is essentially just our frequency. It's really that straightforward. We just plug that in. And so, of course, we really need to justify that this is a simple pendulum. So the second part of this question is sort of getting at that question. And it asks, what is the maximum angle that this is going to swing through? And so we want to solve for that maximum angular displacement. And then once we have that, we can decide if that's small, then this is true. And so it'll turn out that that's the case. So this here is our frequency. But we really want to show that now. So for the second part of the problem, we look for this angular displacement. And in order to do that, we can see we have an inelastic collision occurring here. Ball A is going to fall down, stick to ball B, and then they're both going to rise up here and then start swinging in this pendulum motion. So therefore, we have a problem we have dealt with many times before, which is sort of some inelastic collision. And even moreover, we know as soon as we drop ball A, the only force acting is gravity. So we can use energy conservation to get the velocity just as it reaches ball B. So we're going to go ahead and start by doing that. So we're going to start with energy conservation, where we basically say, let's find the velocity of ball A just before it collides with B. And we know, of course, this starts with some gravitational potential energy, mgh, and that will get converted entirely to kinetic energy. And of course, we're assuming that this right here is our 0 point for height. So we can solve for our velocity of ball A just before the collision, and we should get an answer that the velocity is 1.4 meters per second just before the collision. And then again, we've done this a bunch too. We have basically one ball which is moving with some velocity to the left, colliding with a stationary object. So we know in that collision, we're going to have momentum conservation. So we can go ahead and say our initial momentum will basically be mass A times the velocity of A just before the collision. And then that has to be equal to our final momentum just after the collision, which will be both of these moving to the left with some velocity, which I'll call V0. So this is the velocity just after the collision. So we can again go ahead and solve directly for V0 with what we know. And we should get that V0 is equal to 0.56 meters per second. So that's to say we have the velocity of this clump of balls after the collision. And then from here now, we just want to get back to the maximum angular displacement. So what we can do to move on is we can actually sort of use this energy conservation again. Because after this collision, we know energy, mechanical energy, will be conserved at all times because, again, the only force acting there that we're worried about is gravity. And that will be conservative. So we can then say we have some kinetic energy, which will be 1/2 times both of these masses now since they're stuck together, times our velocity squared. And so this is our initial kinetic energy just after the collision. And when this becomes a point where it is at its maximum angular displacement, this must all be converted to our potential, gravitational potential energy. And I'll call this H final here just to denote that it's different than this H here. So this is basically just the reverse of our beginning equation. And from here now, we can basically solve for how high this clump will get to. And you should be able to get H final is equal to 0.016 meters. And I'm going to box this at the moment because this is almost our answer, right? We wanted to find the angular displacement, and we actually just have a height, which should certainly be related to our angular displacement. So at this point, we can go ahead and move over here and redraw this scenario now, how it stands. So we have some ceiling, and we know just after the collision, this will represent both of the balls now. It's going to be moving to the left, and then it will rise to some angular displacement, and let's assume this here is our maximum theta. I'll call that theta m. And now what we want to do is we want to solve for that theta m, given that this height here is equal to 0.016. So what we can do is let's look over here. We know this is our 0.016 meters. And we also know that this string has a total length of 0.5 meters. So we know this picture is of course exaggerated because if we do our math, we should say this portion of the string has to be equal to 0.5 minus 0.016. So make sure you guys are following along at home here, but then you get this should be 0.484 meters in distance. And so this is useful now because what we can do is we can draw a dotted line right here, and then we can show that given, let me highlight this triangle here is what we want to look at. We know our distance here is 0.484, and then this right here is just going to be a length L. This is just our string, so 0.5. So let's go ahead and redraw just this triangle, which is to say we have a triangle of one side 0.484, of the length here 0.5, and then theta m. So from this, you guys could just do some simple trig, and you should be able to say cosine of theta m is equal to 0.484 divided by 0.5, and therefore our maximum angle of displacement should be equal to 14.5 degrees. And so now this is the maximum angular displacement, and sort of the only step left is maybe to justify our assumption of a simple pendulum. And the way we can do that is by assuming that, of course we made the assumption, I should say, that sine of theta is approximately equal to theta in terms of, in order for this to be a simple pendulum. So what we can do is we can convert this to radians, because this is true only in radians. So let's convert this 14.5 degrees to radians, take the sine of that, and make sure that that is approximately equal to theta. And so you guys can do that at home, and you will see that these are approximately the same. Okay, so let's review what we've done here. We first assumed that the scenario was a simple pendulum, and therefore the frequency depended only on the gravity and length of the string. We solved directly for that frequency. Then we used energy conservation to find the velocity of mass A just before the collision, and then momentum conservation to find the velocity of the masses after the collision. Finally, we used energy conservation again to find the maximum height that the masses would reach, and used trigonometry to convert that to a maximum angular displacement. Okay, so I hope this video is helpful, and I hope you have some better understanding of the simple pendulum. So if you have any comments on this video or any of the videos here, please leave those on the comments link to the right of the video link, and also please fill out the video survey on TED. Thanks for watching.